So, yesterday we were discussing the proof of the Varnamides theorem, which I shall complete, but I shall again review the initial portions so that it is clear, and then we will proceed to proving Roth's theorem from Varnamides theorem following the method of Croot and Sisask. Okay, so this, as I have said already, inverts the historical order of things which went in the opposite direction. First Roth theorem and then Varnamides theorem. So let me restate this theorem for you. So the theorem of Varnamides is let n greater than or equal to 1 be an integer then for any a subset of 1 to n with Ta not equal to 0 and any integer m then m less than n, we have Ta is bigger than or equal to the cardinality of A divided by n minus r of m plus 1 m plus 1 by m divided by 4 times m to the power of 4 times n square. Okay. So, for any m between 1 and n, if A has at least one non-trivial 3-term AP, so Ta, I recall, is the number of non-trivial 3-term APs in A. So, if A has at least one non-trivial 3-term AP, then for any integer m between 1 and n, you have such an inequality. The way this inequality is written is meant to indicate that this is some proportion of n square. So, it tells you that if there is at least one non-trivial 3-term AP, at least the first application of Varnamides theorem was to say that if you have one 3-term non-trivial 3-term AP, then in fact you have many, and actually as many as one would expect up to a constant which might be smaller, but the order is n square. That I will indicate precisely what this means when we finish the proof of this. Okay, so it tells you that if there is one, there are many. That was the original intent. Pardon? RM is the cardinality of the, so it's the supremum of the cardinalities of A such that A is contained in 1 to m and Ta is 0. So, yeah. So, it's the size of the maximal subset of 1 to m which does not contain a non-trivial 3-term AP. Okay, the size has to be the same for any one of the largest size, and that is called R of m. Of course, yesterday we have proved that R of m is subadditive and that Rm by m, the limit exists, and we stated Roth's theorem in weak form, which is what we will prove as that limit is equal to 0. Okay, and the first step was to prove this theorem of Varnamides. So let us go over the steps from the last lecture, just the steps. I shall fill in some details if I have left them out yesterday. So the steps of the proof. Okay, so this is the proof carried out in many steps. So step one was to say the inequality. Maybe I will actually give it a number this time, or I don't know. The trouble is I won't be able to remember exactly that I have given it a number, but let us say 1 just for the sake of reference. The inequality 1 is trivial when n squared by n power 4 m power 4 is less than or equal to 1. Okay, that is simply because this fraction that is written here is less than the fraction without this term here, and this quantity is less than or equal to 1. By definition, A is a subset of 1 to n, and if this is also less than 1, then the entire product is less than 1, and TA is not 0 and an integer, so it's greater than or equal to 1. So you see that the inequality is obviously true. Okay, so therefore we may assume suppose that n is larger than or equal to 2m squared. Of course, I have swiftly computed the square root of both sides here. Okay, that's right. So we may assume that n is bigger than 2m squared. Okay, the second step involved the overcounting argument or the amplification step. So this is the amplification step. So we introduce two families. So we say let F be the family of non-trivial 3-term APs in 1 to n, and let beta be the family of m-term APs of common difference d less than or equal to k in 1 to n. So I just, because I will choose this k at the end, I will write that in a different color. Here k greater than or equal to 1 is an integer that will be chosen later. Okay, so this is these are the two families, and with this, when one applies the overcounting lemma, one has to first count how many for each b in this, or rather for each f, for each non-trivial 3-term arithmetic progression, a uniform bound for the number of m-term arithmetic progressions that contain it. The L that was there in this. So we note that the sum B contain F, so B varying over B of 1 is less than or equal to m squared, which is L for all f in f. Okay, so what this means, the sum means is it counts the number of m term APs that contain a given 3 term AP, and this is a uniform bound. It says that it's less than m square, which I fix to be L in the application of the overcounting lemma. Okay, and why are there m square, at most m square m term APs that contain a given 3 term AP? It is simply because if a 3 term AP, if x, y, z is a 3 term AP, is a 3 term AP, then to determine the number of m term APs that contain x, y, z, you have to only fix the position of say x and z in an m term AP, and that AP is determined because if a plus I d is x and a plus j d is z, then I and j, knowing I and j, you immediately determine a and d. Therefore, the m term AP is fixed. So all you have to do to determine the number of m term APs that contain a given 3 term AP is to count the number of positions the x can take, which is m, and the number of positions that z can take, which is at most m. Okay, and therefore the total number is less than m squared. This is a very trivial kind of bound. You can improve it slightly, but it's irrelevant for our purposes. Good. So with these two observations, with these two families chosen and that observation, the amplification step then gives you we obtain from the amplification lemma we then conclude from the amplification lemma that T of A has the lower bound 1 over m squared times the sum T of A intersection B, B in B. So this was the lower bound we obtained using the amplification lemma. We said that we can introduce this family and actually amplify this TA for the lower bound. So now we go to the next step where we observe that if cardinality of A intersection B is larger, each B is an arithmetic progression of m terms. We then observe that if the cardinality of A intersection B is larger than Rm, strictly greater than R of m, then this T of A intersection B has to be greater than or equal to 1. Okay, so this sum is bounded below by 1 over m squared times the number of B's in B in beta, which is which are such that the cardinality of A intersection B is strictly larger than Rm, right? That was the thing. So I'll write that down as the next step. So step 2, step 3, and that is if we remark that cardinality of A intersection B strictly bigger than R of m implies that T of A intersection B is greater than or equal to 1 for all for any B in B. Okay. Now, why is this? I told you that this is just basically the definition of these things like Rm and so on. At any rate, I'll recall why this is the case. So, B is an arithmetic progression of m terms. That means that there is a map, there is a bijection phi from say 1 to m to B given by phi of k equal to a minus d plus kd, which is of course the same as a plus k minus 1d, right? So 1 to m goes to b because b is, you recall that this b is an AP of m terms. So because it's an AP of m terms, there's a bijection from 1 to m to the AP, right? And that bijection is given by a homothety. A minus d, the constant, the ratio of the homothety is d. Okay? And we see also phi of x, y, z, x, y, z in 1 to m is a non-trivial 3-term AP, 3-term AP is equivalent to this, is equivalent to phi of x, phi of y, phi of z being this is equivalent to phi of x, phi of y, phi of z is a non-trivial 3-term AP in B, right? That's the equivalent statement. And in B is not so important, it's just that this is the case. Okay? And now, since phi is a bijection, now if cardinality, if T of A intersection B is 0, if T of A intersection B is 0, this implies therefore that T of phi inverse A intersection B is also 0 because of this statement, because phi takes 3-term APs to 3-term APs, and this would imply that the cardinality of phi of A inverse B by definition of Rm, this cardinality is less than equal to R of m, because any subset of 1 to m which has more than Rm elements has a 3-term AP. That's the definition of Rm. So that would mean this cardinality is less, but phi is a bijection, so it preserves cardinalities. So that means that the cardinality of A intersection B is less than Rm. Therefore, if you assume that the cardinality of A intersection B is greater than Rm, then this condition must be false, in which case you have it, which justifies, from which our remark follows. Okay, so we see that we only have to count the number of B's in the family B such that A intersection with B is bigger than some particular number which is R of m. Once you count this, you get a lower bound for this family. So let us write, therefore summarize this by saying that using step 3 and this particular inequality, okay, now that I am into numbering things, I may as well call this 2. Okay, so using step 3 and 2, or maybe so here using step 3 and 2, we have T of A is greater than cardinality of C by M square, where C subset of, or C, or I don't know, whatever you want to pronounce it, subset of beta is the family of B in beta, such that A intersection B, the cardinality, is strictly larger than R of M. So now one has to bound this from below, and for that you use the first moment method, which tells you that if you want to bound this B, so if you have a function on a set and you would like to bound from below the number, the cardinality of the set on which the function is big, then you first find the mean of the function and then separate that into two parts where the function is big and the function is small, and then you use Chebyshev bound, Chebyshev argument to get this. So that's the first moment method. Of course, you don't have to know the first moment method to follow what I'm going to do. It's just that it's a standard principle. It's not some trick that anybody devised for this particular case. So it's a very useful method. So to do that, we will have to look at the sum. Step 4 would be to consider the sum. So we shall obtain a lower bound for cardinality of the family C, and this would become step 4. Okay, we consider the sum cardinality of A intersection B of B belonging to B. Now this can be written as D less than or equal to K, because B consists of arithmetic progressions of M terms of common differences less than or equal to K. So you can split this set into subsets based on the common difference. So this times the sum B in B beta D A intersection B, where beta D is the set of M terms with APs with common difference D, where beta D is the set of B and B beta with common difference def of B is D. Okay. Now one can write this further, just to you introduce how to write the A intersection B using the characteristic function of, let's say, B. So this can be written, so sigma cardinality A intersection B, B in beta D. This can be written as the sum of A in A, sum of B in beta D, 1 of B times or acting on A. Okay, so for each A in A, you see it will tell you if this is the characteristic function of B, and so unless A is also in B, you won't get a 1, and you will get a 1 in that condition, and therefore it will exactly count for you A intersection B. Is all. I mean, I'm at some point I'm beginning to accuse myself of writing too much, but nevertheless, just because it's the first time, I'll probably write the details. So here, therefore, if you combine this relation with that, you conclude hence that summation cardinality of A intersection B of B in beta is equal to sigma D less than or equal to K, sigma A in A, sigma B in beta D, 1B of A. Okay, and let us call this 3 for the moment. Now, how does one bound this from below? So, that was the fifth step, more or less the place where I stopped yesterday. So, now what one does is to identify a subset which makes this sum big, and then use that to get a lower bound for the left hand side. Okay, so step 5 is to we note that each A in the interval uh, 1 plus m minus 1 d to n minus m minus 1 d is contained in exactly m arithmetic progressions of m terms and common difference d. So now not only have we fixed the number of terms, we have also fixed the common difference to be d. So each A in this interval is contained in exactly m APs. So it's each A in this interval is contained in a large number of arithmetic progressions of common difference d and m terms. Okay, an m term AP with common difference fixed and number of terms fixed is determined as soon as you determine the position of any one term, meaning the number of such APs where a given A in this interval is in the first position is 1. Okay, the number of such APs where a given A is in the second position is 1, and so on. So you just have to determine the position of A, and then that particular m term AP is fixed. And you see from these numbers that are given here that these exactly m term APs arise because of the fact that you can start from A. So maybe I should just draw it here, or perhaps I'll go back to the end. Boy. So you see that you start from A and you go backwards, A minus D, A minus 2D, and so on, or you go forwards, A plus D, A plus m minus 1D, or you start with A as the second term and you have A plus D, A minus D, and so on. Every such possibility is allowed because A lies between these two numbers. So if you started from here and went back m terms with common difference D, you would still remain in the interval 1 to n because A is larger than this. And same way, since A is smaller than this, if you started from A and went m terms forward with common difference D, you would still remain in the interval 1 to n. Okay. Therefore, there are exactly m APs of m terms and common difference d. Therefore, this particular sum, it follows that then this sum is greater than or equal to. So, you see that thus sigma A in A, sigma B in BD, beta D 1 BA is larger than or equal to m times A intersection ID, the cardinality of A intersection ID. Because for every element of A which is contained in ID, there are m APs and of m terms with common difference D. So those m will give you a 1 here, and they are exactly m, and you get that m from this sum, and you get this. So, pardon? Okay, I didn't say that this interval is called ID. So I call this particular interval ID. Okay, so yep. Therefore, consequently, your sum from 3 gives sigma cardinality A intersection B, B in beta itself is greater than or equal to sigma D less than or equal to K m times cardinality of A intersection ID. Okay, and now what's the lower bound for the cardinality of A intersection ID? It's the simplest sieve statement that you will have. I mean, when I say sieve, nothing complicated, the sort of things we see in school, namely to use the fact that cardinality of A plus cardinality of ID minus the cardinality of the intersection is equal to the cardinality of the union, which is contained in 1 to n and is therefore less than n. Okay, and therefore you see that cardinality of A intersection ID is greater than or equal to cardinality of A plus cardinality of ID, which is what is the cardinality of ID? It is the difference there plus 1. So it is n minus 2 m minus 1 d here, then plus minus an n. Okay, and that would give you cardinality of A intersection ID is greater than or equal to cardinality of A minus 2 m minus 1 d, which is certainly greater than or equal to cardinality of A minus 2 m k, because d is less than or equal to k. Okay, and so you see that the cardinality of A intersection ID is trivially greater than or equal to this much. So you may substitute that here to finally get a lower bound. So you get the lower bound summation, hence sigma A intersection B, B in beta is greater than or equal to the sum of D less than or equal to K m times cardinality of A minus 2 mk. None of these depend on D, and therefore you can just rewrite this as greater than or equal to mk times, because this lower bound for A intersection D is independent of D. So it's just the number of terms times this. So this, let's call this 4. So we have now a lower bound for this sum. Now we have to extract from this a lower bound for that subfamily of A intersection B, consisting of all those B's for which A intersection B is bigger than R of M. Okay. So how do we do that? The first moment method tells you that you have to rewrite this as cardinality A intersection B is now less than or equal to, for those B's that belong to the class C, to the family C, A intersection B is less than or equal to the cardinality of B, which is M, because B is an AP of M terms. Okay, so you get this is less than M times the cardinality of C plus the complement, which is the cardinality of B minus C, beta minus C. For this, anything lying in the complement, A intersection B is less than or equal to R of M, right? So you have here R of M. Because here you want to note that this is because A intersection B is less than or equal to Rm if B is not in C. Okay, so it's this. Now therefore you may combine, now this cardinality of B minus C is just bounded by the cardinality of B itself. So this is M times the cardinality of C plus Rm times the cardinality of B, beta rather. And what is the cardinality of beta? Beta is the set of all M term arithmetic progressions in 1 to n with common difference up to k. Okay, so for the first, if you fix a common difference, say d, then you only have to determine the position of the first term to know the arithmetic progression. And in the interval 1 to n, there are n maximum n such positions. And then the common difference varies up to k. So the cardinality of beta is trivially less than or equal to n times k. Okay, so the cardinality of beta is trivially less than. So I'll just write, we easily see that just because the argument is simply a simpler version than the AP counts that we've been doing so far. So we easily see that the cardinality of beta is less than n times k. Therefore, on combining 4 with this, on combining 4 with 5, with 5, we get what? We get Rm n k. So you will have from this that cardinality of C is greater than or equal to k times cardinality of A minus 2mk minus n divided by m minus n divided by m times Rm. Okay, if I have not made any goof in just combining these two and dividing throughout by m, capital M, you will end up with this, because here you have an nk. Okay, so I have forgotten a k here. So I can write the k outside and write it like this. Okay, because there's an nk here for the beta, and then there's an m sitting here which I have divided throughout. So this m gets cancelled, and I get an m in the denominator in the other term. Okay, so that's that. Now I'll even remove the n outside, so I'll get n times k times cardinality of A by n minus 2m k by n 2m k by n minus Rm by m minus Rm by m. Okay, am I making a mistake? No, so far I think I'm not goofed, and now I should get the answer. So now I choose my k to be equal to the integral part of, so we set k equal to the integral part of n by 2m square, which we have seen from step 1 is greater than or equal to 1, okay, which is greater than from step 1. So this is greater than or equal to 1, and therefore thus you have that k is greater than or equal to half of its value, half of the inside value, which is n by m square, and is less than or equal to n by 2m square. Okay, because k is bigger than or equal to 1. So now if I put that in here, I am going to get, so we conclude that C is thus the cardinality of C is greater than or equal to, from what is written there, you have to substitute in this equation, this inequality, which I call 6, then I will get here n square by 4 m to the power of 4 minus minus here cardinality of A by n minus 2mk by n, and that is 2m by n times n by 2m square minus r of m by m, and this cancel here, so that gives you an m, and this cancels here to give you therefore 1 by m, and in cardinality of C becomes 2m square. Okay. Okay, so you get this. Therefore, you have n square by 4m square times the cardinality of A by n minus r of m plus 1 by m in the bracket like this. Okay, you get this, and then if you call this 7, then you will realize that if you combine 7 with 3, if my memory is correct, is 3 the inequality that says cardinality C is bigger than, I mean the T of A is bigger than cardinality of C by m square. I am assuming 3 is that inequality. Well, so now combining with 2, is it? Okay. So anyway, combining with TA is greater than equal to cardinality of C by m square, we get the inequality stated in the theorem. Okay, so you get this inequality. So if you combine with this, you will get that TA is bigger than n square by 4 m power 4 times cardinality of A by n minus. All right. So it's an elementary argument completely. It just uses the first moment method and overcounting, which are two very standard combinatorial tools. But to use it in this context was Varnamides' contribution to the thing, which is a nice idea to overcount with m term APs and then establish this inequality. Yeah. Pardon? No, it's the integral part of x. Integral part of x is larger than x over 2 because x is a number bigger than or equal to 1. Okay. So, yeah, I'm assuming that I have not made some goofs in the way of proving this. Okay, so now let's look at the usual application of Varnamides' result. But I still have 55 minutes to go. Not bad. They forgot to start the clock, I think. So too bad, you'll all have to sit till they change that. So, so the usual application of Varnamides. So application is, let me recall the bound. So if TA is not equal to 0, then TA is bigger than 4 by m to the power of 4, cardinality of A by n minus Rm plus 1 by m times n square. Now let me just be a little slack and remove the 1 by m simply by, I mean I needn't do it, but I just do it in any case. So I will get this is greater than cardinality of A by n minus 2 times Rm by m divided by 4 times m power 4 times n square. Now suppose I am given an A with cardinality of A greater than delta n. So suppose, okay, and this inequality is valid for any m between 1 and n, and now Roth's theorem tells you that if n is large enough, if n is greater than, we have seen exponential constant by delta, then implies TA is not 0, right? It tells you that TA is not 0 if this is the case. So since TA is not 0, Varnamides inequality is applicable and you get this. Now the question is, this is valid for all m between 1 and n. Now to find out what is, I mean to get Rm by m, I have to choose m appropriately. So I'll choose m for the same thing with delta by 4. So you see for delta by 4, it tells you that Rm by m is less than or equal to delta by 4 if m is larger than exponential 4 constant delta, okay. If any subset of 1 to n has more than delta n elements, then if n is larger than this, TA is not 0. Now apply the same thing to m and write it in the contrapositive. So if any subset is greater than delta by 4 m and m is larger than this, then that subset has a non-trivial 3-term AP, which means that R of m should be less than delta by 4 m if m is larger than this, Of course, R of m will be even much smaller, but it's certainly less than delta by 4 if m is larger than this. Okay, so you put m equal to exponential 4 constant by delta and take Rm by m less than or equal to delta by 4 into this inequality, and then you will get, if you do that, you will end up with Ta is greater than say delta minus delta minus 2 times delta over 4 divided by exponential 16 constant by delta times n squared. So if we then get that if cardinality of A is greater than delta n and n is large enough, that is, this implies that Ta is larger than, here you get delta by 2 times exponential 16 constant by delta times n square, under the hypothesis that cardinality of A is greater than delta n and n is larger than this number, right. So if A is greater than delta n, not only does A have non-trivial 3-term APs, it has a large number of them. It has something that depends only on the density times n square 3-term APs. And n square is the expected number of 3-term APs, because in a 3-term AP, if you choose 2 terms, the third is determined. And if the AP lies in 1 to n, then there are possibly at most n square ways of choosing 2 terms, right. So this was the actual application of Varnamides theorem to tell from Roth's conclusion that in fact not only do you have one AP in any such set, you have a large number of them. Okay, and now we are going to invert this argument, not this one, just the inequality that is stated, to actually go to Roth's theorem in the form Rn by n, the limit goes to 0. So to do that, we will need some Fourier, elementary Fourier analysis. So this is where the combinatorics kind of ends, not really, but just purely combinatorial arguments end, and one uses analytic arguments from Fourier series. So I mean elementary finite Fourier series, and it's starting from this point on that topics like the large sieve that Chatardel is covering, or the Selberg sieve that Stefan is covering, come into this subject. Okay, so we'll just prove Roth's theorem, which will not involve doing any of these things. But when we want to do Green's theorem, then one uses the methods that are being developed in the course on sieves by Chatardel and Stefan. So since we have very little time, let me summarize quickly the Fourier. So let me call this, say, section 2 or so. I call this Fourier Facts. I mean, they're just too trivial to be called anything else. So we will work only with let f from Z to C be of compact support, of finite support rather. What finite support means, that f is 0 outside a finite set. Okay, there's only a finite subset of Z on which f takes non-zero values, otherwise it's 0. Okay, then the Fourier transform of f hat t, or sometimes I'll write f hat alpha depending on the thing is let me say fn e to the 2 pi I n t. Okay, I'll just put a minus sign following standard convention and write it like this. So it's f of n e to the 2 pi I n t. Okay, and this is a finite sum because f of n is 0 for n outside a finite set, so it's a trigonometric polynomial. Okay, this is what I'll just call the Fourier transform of f. Now, a certain number of standard things are there. Okay, so then one also defines together with this if G is also of finite support, then f convolution G defined at n is the sum of f of m G of n minus m m in Z, and it is easily checked that this by changing n minus m to k, for example, is the same as n minus m G of m m in Z, which tells you that the convolution is the same whether you take it. So the order of the two functions doesn't matter. Now, an important property of the convolution is that it is trivialized by integrals. It's trivialized here in the context that we are interested. Integrals are just sums. So we have note that at sigma n in Z, f convolution G times n of n is the same as sigma f of n in Z times so integration or summation trivializes convolution. Okay, so that's one thing which is easily established by summing additionally here over n, interchanging the sum, and then the two it splits into the form that you see. Okay, also we check that the Fourier transform of f convolution G at t is the product of the Fourier transform of f and that of G. So this is also to be noted. Finally, one considers the Plancherel theorem, which follows from the fact that exponentials are orthogonal. So since we have integral 0 to 1 e to the 2 pi I m t dt is equal to 1 if m is 0 and 0 if m is not equal to 0, we obtain what is called the Plancherel or Parseval formula f of t square dt from 0 to 1 is the same as the sum of f of n whole square n in Z. So this follows by the usual way of writing this as f of t into f of the complex conjugate of t, then f hat of t times the complex conjugate of f hat, and f hat, and since f hat is a finite trigonometric polynomial, you multiply out the terms and apply this orthogonality of exponentials to arrive at the conclusion that's given. So this is called Plancherel or Parseval, whatever you wish. So you have this. Now one very simple fact that we will use repeatedly is the observation that if f is positive, if f of n is greater than or equal to 0 for all n in Z, then the L infinity norm of the Fourier transform of f is equal to the L1 norm of f. Okay, because the L infinity norm, which means the maximum of supremum of f hat t in absolute value, that by the triangle inequality that is less than or equal to the sum of mod fn. In general, this is the case by the triangle inequality, but fn is greater than or equal to 0 by assumption. So this is the same as sigma fn n in z, which is exactly equal to f hat of 0, and therefore the supremum is equal to the value at 0, which is also equal to the L1 norm of f. Okay, so this is a fact, this is a completely trivial application of positivity we will use repeatedly. It's helpful to remember this. Okay, so pardon? Yeah, but then I am assuming f is positive, so this is equal to sigma fn, which is f hat 0. So this supremum must be therefore equal, if you want to put this as equal. Okay, so having assembled these small facts, we will now proceed tomorrow to analyze the number of 3-term APs from the point of view of Fourier analysis, and then we will combine this with the Varnamides theorem to conclude the result. Okay.